Welcome to Resoundingly Human, the Informs podcast. I'm Ashley, and in each episode, we explore how operations research, analytics, and data science are helping people make smarter decisions and solve complex problems. Few topics generate more debate than elections, but long before voters head to the polls, important decisions have already been made about how communities are grouped into districts and how representation is structured. While redistricting is often discussed as a political issue, it's also a fascinating operations research problem, one involving competing objectives and complex constraints such as geography, population, representation, and legal requirements, as well as competing definitions of fairness. My guest today, Ian Ludden, Assistant Professor of Computer Science and Software Engineering at Rose-Hulman Institute of Technology, will share how computational methods and ORMS are helping researchers evaluate district maps and better understand the choices that shape our democracy. We'll explore questions of fairness, representation, and how data-driven approaches can help us better understand one of the most consequential and often controversial processes in American democracy. Ian, welcome to the Resoundingly Human podcast.
Thanks, Ashley.
For listeners who may not be well-versed in the history and importance of electoral maps, what exactly is redistricting and why does it matter so much?
Yeah, it all goes back to the foundational decisions of structuring the United States of America, right? As a representative democracy. We have this principle that we refer to as one person, one vote when it comes to the U.S. House of Representatives, the idea being that each representative in that body roughly represents the same number of people. And so every 10 years, the U.S. Census updates population data, and that leads to a new apportionment. Which states get how many districts? Since there's a fixed number of representatives in the House, those have to be potentially reallocated with population shifts. And so then going back to 1812, redistricting already started to have some partisan bias in it with Massachusetts case, where the governor, Elbridge Gerry, approved a map that was had a sort of salamander-shaped district that was called the gerrymander and political cartoon, and the name stuck. And those district lines affect how well different communities are able to voice their concerns, both at the state and federal levels. And it has ripple effects on public health, environmental health, local economic development, education, and all sorts of other public policy decisions. And recently, we've had this mid-decade redistricting push, which is a little unusual, driven by parties trying to consolidate power before the midterm elections, and has been compounded by the recent Supreme Court case in Louisiana.
I remember learning about gerrymandering in school, and then as an adult seeing an actual salamander and thinking, that's kind of a stretch, but I get what they were going for. Yeah, exactly.
Political cartoons are often a stretch.
Yes. All right, Ian, your research sits at sort of the intersection of operations research, computer science, and public policy. How did you first become interested in applying quantitative methods to questions of representation and elections?
Yeah, so when I started looking at grad school, I knew I liked graph theory and graph algorithms and their application to tangible problems. And when I got connected with Sheldon Jacobson at the University of Illinois, I saw that his lab had a rich tradition of OR and CS applied to public policy, such as Laura Albert's famous work that helped influence TSA pre-checks design. And in conversations with other students, I came across a paper that connected fair cake cutting, the idea that if you and I want to share a piece of cake, I can cut it into what I think are two equal pieces, and then you can pick which one you want. And they connected that to redistricting. And I found it a fascinating paper. So I started there and then went from there and collaborated with other folks in the lab. Another big thing for me as my involvement in this work has progressed is I find it a great way to try to make an impact on society with some positive change and align with my values and align with human dignity. And my faith helps inform that with, most recently, Pope Leo's encyclical that touches on AI a lot, but also has some broader points. He calls on developers of technological tools to embed values in their projects with transparency and responsibility toward affected communities, and making sure that what we're cultivating is actually a genuine common good. And so that really helps inform a lot of my work.
Yeah, I love that, OR for good. I know both Laura and Sheldon very well. They have both also appeared on the podcast several times. Many people think of operations research in terms of supply chains, transportation, or business operations. What makes redistricting such a compelling ORMS problem?
Yeah, it deals with some core problems that we're familiar with from classical OR. You've got graph partitioning, you have these connectivity constraints and population balance constraints. And there's a lot of interesting variety of objective functions to consider, often that come from political science communities, and they're interesting to try to represent mathematically in a way that's amenable to optimization models. There's also a lot of data available, both from the US Census and then from election bodies, not-for-profit organizations, academics are all kind of aggregating data. And it's at a fairly large scale that makes it interesting to try to design effective optimization techniques.
One thing that I think surprises people, and honestly, it was kind of a surprise to me when I was researching this interview, is that there isn't a single universally accepted definition of a fair district map. Why is fairness so difficult to define in this context?
Yeah, this question really gets at the root of voting and representation systems. If a group of people have different individual preferences, how can you aggregate that into a single choice that reflects their collective decision? And Kenneth Arrow famously showed in the early 50s in his so-called impossibility theorem that really there's no perfect solution if you make certain assumptions and have certain goals that you state. And so in the context of redistricting and representative democracy more broadly, political scientists have come up with several different ways of quantifying fairness usually based on the expected outcome of near future elections. And probably the most intuitive is proportionality, where each party's fraction of seats that they win in that state should roughly match their fraction of votes that they get in the statewide elections. Some European political systems actually guarantee proportionality through the design of their voting systems. But in the US, most states have single member districts with plurality voting or first past the post voting, and that doesn't guarantee proportionality at a state level or at a federal level. Another more recent suggestion from some political scientists is called the efficiency gap, where you measure the difference in wasted votes between two parties across a state's districts. And a vote is considered wasted if it's above 50% plus one person, or if it's cast for a losing candidate. This tries to sort of measure the effects of the two main methods of gerrymandering, of packing, where you force a bunch of your opponent's voters into one district so that they're kind of wasted above an excessive win, or cracking, where you spread your opponent's voters thin across a bunch of districts so that you get a lot of narrow wins. Unfortunately, the efficiency gap has several paradoxes and is heavily disputed in the political science community. It was used in a Wisconsin redistricting case back in 2017, 2018, but hasn't been settled on as a standard metric. Another challenge with quantifying fairness, though, is that the real world's messy, and so it doesn't always play nice with our cute formulas that try to shrink fairness into a single number. Geographic voter patterns, for example, can really affect things. So in Massachusetts, about a third of voters tend to vote Republican in statewide and federal elections, but they're so evenly spread across the whole state that it's impossible to make any one of the 9 congressional districts lean Republican with the current distribution.
That really makes it very clear why fairness is such a hard, how it's so hard to define in this setting. When you're evaluating a district map, what are some of the key criteria that you consider?
Yeah, so one of the first things is contiguity, so geographical connectedness of each district. You should be able to drive to your representative and complain about whatever your concerns are directly. Sometimes, in states where there's islands, you need to cross water to get that geographic connectedness, but that's a pretty standard requirement. There's also population balance, and that goes back to the one person, one vote principle. How close is each district's population to the ideal for that state, where you just take the statewide total population divided by the number of districts. There's also compactness. How reasonable are the shapes of the districts? For this, I like the graph cut edges metric, where you look at the adjacency graph of all the units and see how many adjacent pairs of units, which could be counties or census tracts, are in different districts. It's really easy to model mathematically, and it avoids some of the problems that you get by trying to force circles or squares or other polygons to fit into real geographies where we have rivers, mountain ranges, and squirrely state borders like in Maryland or West Virginia. Another one is preserving political boundaries, such as counties, cities, and towns, and then also trying to preserve communities of interest, which are a little bit more loosely defined, but are just regions where people have some sort of shared interest or identity that should be preserved and represented cohesively. There's also the Voting Rights Act to consider, which has historically been interpreted as justifying majority-minority districts where certain conditions are met. But there's been a pretty big seismic shift in the application of the Voting Rights Act based on the recent Louisiana Supreme Court case. And then depending on the state, there might be others like preserving cores of prior districts so that you're not making drastic changes to representation from election to election, and then aiming for competitive districts so that representatives are more likely to be responsive to shifts in voter sentiments, or avoiding pairing incumbents so that you're not pitting them against each other in the next election.
So you've touched on a couple of these already, but I'd love to hear, how do concepts like compactness, competitiveness, preserving communities, and minority representation sometimes work together and sometimes probably compete with one another?
Yeah, so one good example here is ethnic or racial enclaves. Often these are reasonably compact due to the natural community development pattern. For example, if you look at, say, Chinatown in San Francisco or Harlem in New York City, clearly a congressional district shouldn't be chopping through Chinatown or cutting Harlem in half. So in these cases, the goals of maximizing compactness, preserving communities, and offering minority representation can line up. But sometimes there might be some tension between these goals. One infamous example is Illinois' 4th congressional district from 2013 to 2023 looked like this bizarre earmuff shape where you had two clusters connected by a very thin strip. And at first glance, you say, oh, that's a horrible gerrymander. But it was actually designed to be a majority Hispanic district, complying with the Voting Rights Act by joining a Puerto Rican neighborhood with a Mexican-American neighborhood.
That's interesting. So I think I already know the answer to this, but is there such a thing as a perfect district map, or is redistricting fundamentally about balancing trade-offs?
Yeah, there's really no one perfect district map. Even if you hyper-focus on one objective, say population balance, by the time the new district lines have been drawn, populations have already shifted since the census. So we're always settling for approximate balance to some degree. And so at the end of the day, redistricting has these fundamental trade-offs, and it's up to each state to say which criteria are must-haves and then which ones are just nice-to-haves, and establish that priority order. One analogy I like to make here is that it's kind of like when a family is planning out meals and groceries for the week. There's no perfect plan, and there's a lot of good options, but you can still say that some are clearly better than others. Just like you can rule out a grocery list that has 10 boxes of cookies but no vegetables.
Sounds like my grocery list. So Ian, your work uses computational methods to generate and analyze large numbers of possible district maps. Could you give us kind of an idea of how this process works at a high level?
Yeah, for map generation, one of the best tools out there is the open source Jerry chain, which has a Markov chain fundamentally underneath, where you start with a seed map, and then you start making random changes to that map in a way that gives you new maps. And if you run that for a really long time, then you get a sense of the distribution of maps, and you can embed that tool within other frameworks that are familiar, meta-heuristics or other local search techniques. And one of the key ideas that's really made Jerry Chain successful is this recombination step, where to get a new map, you start with an existing district map, you take two adjacent districts, glue them back together, and then find a new way to split them apart into two districts, and that changes the boundary between them. And that approach is nicely biased statistically towards more compact districts. So you sort of get compactness somewhat for free, since the districts that are more compact tend to have more spanning trees, and it's based on drawing a spanning tree and then chopping it. And this showed up in our case studies in Missouri and Arizona. We used Jerry chain and the recombination step for a multi-phase local search procedure. With the Arizona case, we used some coarsening as well to speed up the process.
To build on that, the case studies involving Missouri and Arizona, without getting too into the politics of any specific state, what have those experiences taught you about the complexity of redistricting decisions?
Yeah, I've learned that there's really no one-size-fits-all solution, and it's so important to learn from local stakeholders about their particular context. There's really only so much you can learn from satellite images, census data, and past election information. In Missouri, we found, this was a bit surprising, that some of the stated goals of redistricting criteria don't always match up with their effects. So there was a new rule that on the face of it was supposed to improve competitiveness, but it actually led to fewer competitive districts. And this was a case of actually misinterpreting the efficiency gap that I mentioned earlier.
So one thing I find really fascinating is that operations research can't tell us what values we should prioritize, but it can help us understand the consequences of these choices. How do you see the role of ORMS in public policy conversations similar to this, like this?
Yeah, our community is really good at measuring trade-offs in different objectives. When we have a multi-objective optimization problem, we're really good at analyzing sensitivity to different parameters, dealing with uncertainty in data, and all of those skills are really helpful in public policy conversations. We can help communicate what's possible and what's not in particular scenarios, and we can also fact check excuses that are made to justify certain maps. For example, there's a lovely paper from Austin Buchanan's group at Oklahoma State titled "A Widespread Belief About County Splits and Political Districting Plans is Wrong." And they show that it's possible to achieve best case population balance without splitting any counties, which disproved some arguments that had been made in some redistricting court cases.
What does a successful application of operations research really look like in the redistricting process?
It could show up in a few places. It could show up in generating potential district maps, evaluating existing district maps, or assessing the possible impacts of rule changes. And in that sense, there's opportunities to contribute in terms of descriptive, predictive, and prescriptive analytics. So there's something for everyone. And there's always a need for more theory and methodology work too, like new formulations that support faster solving of these challenging districting problems.
So, Ian, do you think we're moving toward a future where quantitative analysis plays a larger role in how district maps are evaluated and debated?
Potentially. We already have some independent organizations like the Princeton Gerrymandering Project creating scorecards for real world district maps. As a response to all of this mid-decade gerrymandering, I think we will see some grassroots efforts to improve redistricting processes and criteria in several states. I think we'll see more efforts that look like Arizona's Independent Redistricting Commission or Ohio's Redistricting Commission, where they have a public submission portal where anyone can draw a map and submit it. And I think these will continue to develop and include some of those scorecards reporting the different nonpartisan and then potentially some of the fairness metrics as well, so the public can easily compare apples to apples.
All right, Ian, it's time for our Ask AI segment where I ask our AI assistant, in this case, ChatGPT, the following question. If you had to draw district maps for an entire state, what would be the hardest part? Mathematics, politics, geography, or human behavior? And AI responded, human behavior. Mathematics can optimize objectives, geography can be mapped, and political rules can be encoded as constraints. Human beings, however, have an extraordinary ability to disagree about what fair means, even when looking at the exact same data. Ian, do you think AI has a pretty good point here?
Yeah, anyone looking at our current, mid-decade gerrymandering surge can see that the human component has been the weak link here. I'm actually reminded of a chapter in the book Political Geometry, edited by Moon Duchin and Olivia Walsh. It's a lovely book, and the fourth chapter, political scientist Keith Gaddy explored the question, is the redistricting problem math, systems, or people? And after cycling through all of those, he lands on it being fundamentally a people problem. He says, unified party majorities have little incentive or reprimand beyond conscience and a sense of fair play to not seek political advantage. So we're kind of getting some of the results that we would expect from the way the system is currently designed in most states.
Okay. All right, Ian, so these are some quick fire questions. Just kind of say the first thing that comes to mind.
All right.
The most common misconception about redistricting?
Probably that crazy district shapes are always evidence of gerrymandering and the only evidence of gerrymandering. The reality is far more nuanced, as I mentioned with the earmuffs case.
Mm-hmm. Yep. All right, favorite optimization method or OR tool?
Yeah, I'm partial to graph algorithms, such as Edmonds Blossom algorithm, that make use of rich combinatorial structures.
Our listeners will know what that is more so than I do, but all right, a public policy problem you'd love to see more researchers tackle.
Yeah, I think we could use more eyes on the housing market challenges. I've seen a couple of nice papers in the Informs journals, Management Science and Marketing Science, but I'd love to see more.
All right, a book you'd recommend often.
Yeah, Mathematics for Human Flourishing by Francis Su. This really helped me rediscover my why during grad school.
Excellent. If you weren't studying redistricting, what OR application area do you think you'd be pursuing?
Probably vehicle routing problems, since I'm drawn to those graph-based structures.
One thing that has surprised you most during your research?
Yeah, I came across the FKT algorithm, named after Castellan, Fisher, and Temperley, some statistical mechanics researchers that back in the early 1960s, they studied the number of ways that you could arrange dimers, two atom polymers, on a lattice, on a grid. And that actually showed up in a redistricting paper I was reading. Daryl DeFord and some others wrote a paper studying the case of Alaska, where the state House districts have to be nested in a 2-to-1 ratio inside of the state Senate districts. And so what that means in OR terms is you have a perfect matching problem if you're given the set of state House districts and you need to form the state Senate districts. And so they use this FKT algorithm, which is a beautiful algorithm that combines sort of graph theory and linear algebra. And it's a great example of making those connections across disciplines. And so for that reason, I now teach this at the end of our undergraduate algorithms course here.
All right, and one final question. In one word, can you sum up the future of computational redistricting?
Illuminating.
See, that was a tough one for one word, but I think you nailed it. All right, before we wrap up, I'll leave you with a thought from today's conversation. Democracy depends not only on the choices voters make, but also on the systems that shape those choices. Ian's work shows how operations research can help bring greater transparency, rigor, and understanding to those systems. It won't eliminate disagreement, and it won't answer every question about fairness, but it can help us have more informed conversations about the trade-offs involved. And ultimately, that's one of the things ORMS does best, helping people navigate complexity and make better decisions. Ian, thank you again so much for joining me on the podcast today.
Thank you, Ashley.
And thank you to our listeners for being part of the Informs community. To learn more about Ian's research, visit the links in our show notes at resoundinglyhuman.com. Until next time, I'm Ashley, and this is Resoundingly Human.